Welcome to Year 8 Competence-Based Middle Years Program Level 3 Sciences. This is lesson number 2. In this lesson, we are going to analyze the basic concepts in circular motions, and we are going to study uniform circular motion, UCM. Let's start thinking a moment about the different circular motions we can find. Uniform circular motion. What will be the shape of its trajectory? Do we think there will be anything constant? And if there is anything constant, what changes during this motion? And what about the uniformly accelerated circular motion? What shape will be the trajectory? Will there be anything constant during the motion? And what changes during that motion? Let's have a moving body that follows a series of points along a circumference. We will represent that succession of points, the trajectory, with a red line. The distance covered is called delta S. At every single instant, we are at the same distance from the center of the circumference, and that distance is called the radius. It is represented by rho, the Greek letter. As we move, the radius sweeps a given angle. We call that angle delta phi, the variation of the angle, phi being another Greek letter. So again, rho is the radius, delta S is the distance covered, and delta phi is the angle swept. We call average angular speed the angle swept divided by the time it takes us to sweep it. We represent it by the Greek letter omega, and the subindex m indicates average. We know that the length of the circumference is twice number pi, 3.14 with endless decimals, times the radius. L equals 2 pi times rho. If we consider that 2 pi is the angle phi, then we will say that L equals the angle times the radius. That angle that covers the entire circumference with a number of 2 pi is expressed in radians. We will go back to that in a second. So, given that the length of the arc is the angle times the radius, we could say that for any circular motion, delta S, the distance covered, equals delta phi, the angle swept, times the radius. The angle has a dimension of 1. This means it is non-dimensional. Therefore, the distance equals the angle times the radius. The angle is non-dimensional, dimension 1. The radius is a length. Therefore, the distance is a length, as we know. Let's now see what the radian is. As we move along the circumference, we cover a given distance equal to the radius. Delta S, marked in red, is as long as the radius. The angle that comprises that arc is called a radian. Let's draw further radians and move along the circumference. We end up having 6.283 radian, which is 2 pi. Therefore, a radian equals multiplying times a conversion factor, who equals 1, 360 degrees per circumference divided by 6.283 radians per circumference. Therefore, we cross over the radians and the circumferences, and we obtain that the radian is approximately 57.3 degrees. We express the angular speed omega in radians per second, or in revolutions or rotations per second, or in revolutions or rotations per minute. The dimensions of the angular speed are the dimensions of the radians per second, which is 1 divided by time, so it is time 2 minus 1. Let's do a problem to illustrate what we just saw. Example 1D, a child rides a merry-go-round that does a full turn in 12 seconds. Find the average angular speed in radians per second, revolutions per second, and revolutions per minute. We will start with the scheme as always, and we see that the average angular speed is the angle swept divided by the time it takes to swipe it. And we are told that it does a full turn, meaning a revolution, in 12 seconds, therefore a revolution divided by 12 seconds. Now we multiply that times a conversion factor. We know that 2 pi radians is a full turn, is a revolution. So if we multiply times 2 pi radians divided by a revolution, that's multiplying times 1, and we don't change anything, but we can get rid of the unit we don't want, which is the revolution. And that equals 2 pi radians divided by 12 seconds, or pi divided by 6 radians per second. That's the average angular speed. To calculate the other units, the angular speed in the other units, we again consider that the angular speed is the angle swept divided by the time it takes to swipe it. One revolution in 12 seconds is 1/12 revolutions per second. And in revolutions per minute, we know that 60 seconds make a minute. So multiplying times 60 seconds divided by 1 minute is multiplying times a conversion factor. It equals 1, but we can get rid of the seconds, and we obtain 60 revolutions in 12 minutes, which means 5 revolutions per minute. When we are riding on a merry-go-round, we can be further or closer from the center. So let's represent 2 children that are going around the merry-go-round on 2 horses, for example, one which is closer to the brim and one which is closer to the center. We will represent that by the 2 dots, whilst the brim is the blue line. It's not a perfect representation because it starts and it stops, but it can serve us to see a little bit what it happens with each of the 2 dots. The outer one will do a turn like this. We see that it goes at a certain speed, and now that's the effect of the PowerPoint. Apologies, it stops. And let's see the closer one. We see that it turns in the same time, but it goes more slowly because it is closer to the center. Let's now see the trajectory drawn in both cases at the same time. We see that as they swipe the same angle, the outer child, green trajectory, covers a longer distance than the inner child with the red trajectory. This illustrates how we can calculate the linear speed, or simply speed. We know that the distance covered is the angle swept times the radius. And we also know that the average speed is the distance covered divided by the time it takes to cover it. Therefore, we replace. That will mean the average speed equals the angle swept times the radius divided by the time it takes. But that is the same as saying the angle swept divided by the time it takes times the radius, and that is the angular speed, the average angular speed, times the radius. The average speeds have dimensions of length times -1. When we multiply the angular speed times the radius, we have times -1, which is the angular speed, times the length, which is the radius. Therefore, length times time -1, as we wanted to prove. Let's finish today's session with a numerical example. Example 1e. The child in example 1d rides a horse 4 meters from the center of the merry-go-round. The younger sibling rides a car further inside, only 3 meters from the center. Find out their linear speeds in meters per second. So let's, as always, represent the situation we have. The outer child covers a longer distance, whilst the inner child, covers a shorter distance when they swipe the same angle, as shown in the image. So V1, the speed of child 1, will be the angular speed of child 1 times the radius of child 1. But the angular speed is the same because they both rotate at the same time, at the same rate. Therefore, we can call that omega, the common angular speed, times radius 1. That is pi divided by 6 radians per second, as we calculated, times 4, which is the radius for this child, which is 2 pi divided by 3 meters per second, approximately 2.1 meters per second. Normally, we do not replace pi by its value. For the second child, speed 2 equals omega 2 radius 2, angular speed 2 radius 2, but the angular speed is the same, therefore it's omega times radius 2, which is pi divided by 6, as in the previous case, times its radius, which is 3. That is pi divided by 2 meters per second, half pi meters per second, which is approximately 1.6 meters per second. And with that, we are done for today. As always, in science and in life, enjoy.